Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. So I'd like to start off our event today by thanking Databricks for sponsoring today's event. Databricks is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now, today's webinar is entitled Applying Convolutional Neural Networks with TensorFlow, and that'll be presented by Databricks. But before we begin, I'd like to briefly review the format for today's presentation. Today's event will be an hour long. We have one presenter, who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's webinar is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. Now, I'd also like to encourage our attendees to provide questions throughout the presentation, so we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Denny Lee with Databricks. Now, Denny is a technical product manager at Databricks. He's a hands-on distributed system and data sciences engineer with extensive experience developing internet-scale infrastructure, data platforms, and predictive analytic systems for both on-prem and cloud environments. He also has a Master's of Biomedical Informatics from Oregon Health and Sciences University and has architected and implemented powerful data solutions for enterprise healthcare customers. So Denny, hey, thank you for being with us today. We're looking forward to your presentation. Now, in today's Data Science Central Deep Learning Fundamentals Series webinar, we'll cover the fundamentals behind TensorFlow and how to apply them within a convolutional neural net. The principles we'll cover include CNN concepts and their impact to the accuracy or loss of your network. Now, all the concepts will be brought to life by demonstrating how Databricks simplifies deep learning, letting you quickly access ready-to-use machine learning environments, as well as prepare data and train models faster. Now, after the session, if you request, you can receive the presentation and associated notebooks so you can run these examples for yourself. So Denny, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Well, thank you very much, Bill. I appreciate the time, appreciate the introduction. Well, let's give this presentation a quick start. As Bill noted, today's session is applying convolutional neural networks with TensorFlow. A little bit about Databricks. We are the company that accelerate innovation by unifying data science, engineering, and business together. Our product is the Unified Analytics Platform powered by Apache Spark. The company was founded by the original creators of Apache Spark. So, as part of the Deep Learning Fundamental series, this actually is a four-part series. We had already in the past done Introduction to Neural Networks, training neural networks, and applying your convolutional neural networks using Keras with the TensorFlow backend. For this fourth session, we are specifically focusing on applying your convolutional neural networks, but specifically on TensorFlow itself. So we're going to do a little bit of a primer, but then we're also going to dive right into the code itself. So we might be switching back and forth between the slides and the notebooks that we're using, because that allows us to dive into the code itself. Okay. So so a bit of a primer first. Let's talk about TensorFlow. Okay. So what is TensorFlow? If you're not familiar with TensorFlow, it is an open source software library for numerical computation using data flow graphs. Okay, this is actually an important concept. It's based loosely on neural networks. It's built in C++ with a Python interface, and it's quickly gained very high popularity. In fact, it became the #1 numeric framework in GitHub within a month of its release, and it supports GPU computation. When we talk about the concept of a data flow graph, think about a graph, except in this case where the nodes are representing your mathematical operations, and the edges of your graph are multi-dimensional arrays. These multi-dimensional arrays are known as tensors, by the way. So thus, if you put those two concepts together, basically the nodes as your mathematical operations and your edges as tensors, the TensorFlow is basically the flow of multi-dimensional arrays, tensors, okay, between the mathematical operations, nodes, i.e. a flow of tensors, and hence the naming convention TensorFlow, okay? And so, again, a little bit on the primer side, let's talk about artificial neural networks or multi-layer perceptrons and diving right into it. So here's this concept of a simplified two-layer artificial neural network. You've got the input layer, you've got one hidden layer in this case, and an output layer, okay? And the example that I like using is do I snowboard this weekend? I'm from the Pacific Northwest, so do I snowboard at Crystal? Do I snowboard at Whistler this weekend? I'm not sure. So there's that part of me, that persona of me, X1, the input, that's the après-skier. In other words, the person who really is only going because I want to go to the after parties, okay? Versus X2 input, which is I'm the shredder. I'm the person that really wants to go to Blackcomb and snowboard, okay? And so the concepts or the inputs in play from the hidden layer, H1, H2, H3, is in this case the weather, how good's the powder, and whether I'm going to have good driving conditions or not. Okay, so using this concept, all right, again, remember the X1, X2, the après-skier persona versus the shredder persona of myself. Okay, input for H1, H2, H3. Again, H1 and H2, H3 is weather, powder, and driving, respectively. So the inputs of one here, so because basically I'm right now, I'm thinking to myself, yeah, I'm actually excited for both concepts, okay? But the weights start coming in. So this is the edges that are starting to come into play of our graph here. All right, and so in this case, 0.8, 0.2, 0.7 for weather, powder, and driving, respectively. Can't guess, that's the après-skier persona, because they care if the weather's good. The powder, they don't really care so much because they're really there for the parties, and if the driving conditions are well, okay? And so versus in green, the edges are in this case, is this, excuse me, is the persona of the shredder. In this case, weather is important, but not as important as the power. If there's a good layer of snow, then I care about that. And boom, driving, I don't really care. I love driving from the Pacific Northwest to Blackcomb, so on the Sea to Sky Highway, so this is perfect. Okay, so these are the calculations based on a sigmoid function, which I'm going to discuss shortly. And then there's our hidden layer calculations. All right, and then now what is the output? Well, again, we start with the hidden layer calculations. Again, now we have our second level of edges here in order for us to do our calculations. So the sigmoid of 1.105 ultimately results in 0.75, meaning that I guess I'm going to lean more towards snowboarding this weekend because between the two personas of après-skier versus shredder, and from the weights that are being applied, I'm leaning much more toward, because you think from a logistic regression perspective of 0 being no and 1 being yes, I'm leaning more toward yes. Okay, so that's a cool way of me explaining a relatively complicated concept of, trying to decide between snowboarding using a very simplified multi-layer perceptron or two-layer artificial neural network. Okay. Now, in addition to this concept, there is this concept called back propagation, okay? Now, in the case of back propagation, this is a common way for artificial neural networks to be able to go ahead and go backwards and restructure or reset the neural network so that we can go ahead and train the system to be more precise or more accurate, okay? And so, for example, when I looked at the system, it's actually, even though I calculate 0.75, in reality, I was leaning more toward 0.85, okay? That's what the real value is, quote unquote, you know, when you're doing these tests. So what we do is we go backwards throughout the system and restructure or recalculate everything. So this error is basically calculated and distributed back through the network of layers. So the weights will start changing between the nodes. So that way our next calculations or next time we go through this process, it'll become more accurate. Okay, so this is the concept of backpropagation, the ability to go ahead and take the note, if you know the real value, go back through your network, propagate that error, distribute it throughout the nodes, so that way you have a more precise value. This is actually an important concept for any neural network that we have, okay? All right, and so now, again, we're going to switch over a little bit to a primer on convolutional neural networks, okay? It's, as noted, it's a neural network specifically designed for images. It's similar to any concept of an artificial neural network, but CNNs or CovNets make explicit assumptions that inputs are images, okay? The reason why is because regular neural networks don't scale very well against images. For example, if you take a standard CFAR10 image, which is 32 by 32 by 3, 32 pixels width, 32 pixel height, and 3 color channels, there's about 3,072 weights, which is somewhat manageable. But if you take a larger image, that's 200 by 3, for example, so it's not even that large yet, it's 120,000 weights. So this exponential growth is that if you increase the pixel size, increase the color channels, filters, whatever else, the larger that image becomes, the more weights becomes. And so it becomes harder and harder and harder for that regular neural network to be able to scale well against that. So because of that, we explicitly design CNNs that have neurons arranged in 3D, width, height, and depth, okay? But the other key concept is that neurons in a layer will only be connected to a small region of the layer before it, okay? In other words, it's not a fully connected matter. It's only going to look at a small set of information. This is very important when we start talking about things like convolution, stride padding a little bit later on, okay? And the final output of the layer for your, for example, your CFAR10 is a 1 by 1 by 10 image, which is then basically because it reduces that full image into a single vector of class scores along the depth dimension. And because you can do something like this, then at that final layer output, that can be fully connected. But prior to that, we're actually only looking at a smaller subset of it, okay? And this allows CNNs to be much more efficient, okay? And so this is a very good visualization of the sources right there of what on the left side, what a regular 3-layer neural network does look like, but then what a CovNet looks like on the here on the right side, where basically your 3D input results in a 3D output, okay? All right, so in this case, we're gonna talk about convolutional neural networks. This diagram that you see here is actually a direct translation of the code. I'm actually gonna present the code to you in just for a second here. And so what you see here right now is actually the code inside a notebook, which you will be able to download and run yourself, okay? So, and what we're going to do is for the remaining 30, 40 minutes of this session is to go through the code itself and then talk about the concepts behind the code. So for example, what is this concept of the first convolutional layer in terms of weights, bias, ReLU, okay? So this, for example, when I look at this, how does that translate? So let's go ahead and actually talk about those concepts now, okay? So here, back to the slides. Basically, we're going to, as noted, we're going to focus on the convolutions, we're going to focus on subsampling, which is the pooling area, and we're going to focus on fully connected. There are other concepts too, but these are the key concepts that we want to talk about for today's session, okay? And so, again, just as a reminder, what is the input? The input in this example that we're using is from the MNIST dataset. It is basically a handwritten digits, okay? Where we're basically translating those handwritten digits into numbers. And so, for example, in this case, we have a pixel value of 32 by 32 by 3, okay, with the value 9, for example, that you're seeing here. That's the input that we're receiving. So what does that input look like? Well, so if you look at the input, basically, if I was to graph out the numbers here, you notice that there's a lot of zeros here on top. But if you look at the 9 here, this is me going ahead and translating the numbers into a color. The larger the number, the closer it is to 1, then you can go ahead and it darkens more of the pixel, basically. So what you see here is the 9 here, all right? And so you can see right here, for example, where I'm pointing, that's a 0.992, because, well, guess what? That's more of it shaded versus a 0 here on the outside, because that's not shaded at all. Okay, so this is a numeric representation in an array/matrix of the number of your handwritten digit. Okay, so that's the input that we're receiving. All right, so now we're going to go ahead and start doing convolutions here. Okay, all right, so the convolutions is basically compute the output or the dot products between the weights. Remember how we talked about artificial neural networks, where we're basically taking the x1 input times the h1, excuse me, the w1's the weights, all right? So this is what we mean by the dot products of the weights with their input, okay? But remember, connect to a small local region, okay? All right, so in this case, if we go ahead and use 32 filters, then the output is 28 by 28 by 32 using a 5 by 5 filter. We're gonna go through those concepts now to explain how we get from 32 filters, why is it 28 by 32, and what's the concept of this 5 by 5 filter here, okay? All right, so again, we're focusing on the convolutions, all right? So remember how we talked about convolutions prior, where we said it's looking at a smaller portion of it. So for example, if you were to look at this particular animated GIF here, okay, the image is on the left side and the convoluted feature is on the right side. So we basically are taking a 3 by 3 filter, that's the yellow box that's moving around on our 5 by 5 image, and the convoluted feature, the output of that is our 3 by 3. Okay, so this is during our forward pass. So we slide over the image spatially, i.e. convolve, each filter across the width and height and compute the dot products. Okay, so this is that concept when we're talking about when we're saying we're only going to look at a small portion of the image on each pass. In other words, we're not trying to look at the entire 5 by 5. We're only looking at 3 by 3 of it at any one point in time. Now, typically images are a lot larger. Even in the case of our 32 by 32 image, we're still only going to look at a 3 by 3 or 5 by 5 or something like that when we're processing it. We're not going to try to look at all 32 by 32 here, okay? All right, so often where you're going to hear the wording or terminology like the kernel or the filter or the feature detector, they're basically all the same in this context. Okay, so this is an important call out here. Okay, all right. So again, there's that concept of local connectivity. You would connect a neuron to only a small local region, as is impractical to connect to all the neurons. Okay, and so when we talk about that dot product, basically, so we described it more from a cell neurological perspective. You've got that W0 times X0 or W1 times X1 that per the artificial neural network calculations that we did, the exact same concepts are applied here. Your cell body is a summation of W1 times X1 plus B. This is the bias. We're not going to go too much into that, but basically that's the concept here. Times an activation function, which we'll talk about shortly, and then that's the output. So remember how we just talked about artificial neural networks and how me as an après skier versus a shredder, how do I do those calculations? Those same calculations are coming, that same type of math is coming into play here, okay? All right, so the goal of our convolution is to create an entire set of filters in which each convolutional layer produces a two-dimensional activation map. So, you know, in this case, I've got 6 filters. For those six filters, then I'm going to have 6 activation maps that have been created, okay? And so here's that specific code right here that was in the notebook. I pulled out the code and included those in the slides here. So that way we can go ahead and call that out, okay? So as you can see here, the definition of our 2D convolution, okay, is simply, in this case, TensorFlow, neural networks, Conv 2D, all right? When we call it, we're basically calling it via the weight variables, our bias variables, and the ReLU. Okay, now let's talk about each of some of those major concepts that we have inside here. First of all, let's talk about the 5x5 here. This 5x5 here is that filter or that kernel that we were talking about. That's the kernel that we just referred to. In the previous slide, that was a 3x3, but here it's a 5x5, okay? And so, for example, when you have a image that's 32 by 32, it will convert to 28 by 28 when you're using a 5x5 filter. Why? Because there's a 5x5 kernel that goes pixel by pixel, right? As you can see here, it's going right by right, and it fills up on the left side is the 32 by 32 image. On the right side is the 28 by 28 output based on using that 5x5 filter. And then hopefully this animated just sort of helps sort of grok how, because you're doing 5x5, how that sort of shrinks down, okay? All right, so that's the first concept. The second concept is the concept of strides, and that means how many pixels are you going to move to the right or to the bottom, right? For example, a stride of a 1, you'll notice that basically this 7x7 image converts into our 5x5 convoluted image, all right? And then if you go a stride of 2, for example, that does work. What ends up happening is that your convolution comes out by a value of 3, okay? But then if you do a stride by 3, it actually doesn't fit, okay? So if you look at basically the output size, it's the n, which is the size of the image. I'm assuming square images, by the way, minus f, the filter, divided by stride plus 1, okay? So in other words, that's how you can do the calculations. And traditionally or typically you'll see the stride being, at least in the earlier rounds, it's going to have a value of about 1 or 2, typically 1, just because you don't want to lose too much information with each pass, okay? So that's why you actually want to slowly and gently get to your smaller or your fully connected layer as opposed to just jumping right away, okay? All right. So that's the concept of strides. And so again, this impacts how your TensorFlow code is going to run. So in this convolutions, we talked about the filter size, we talked about the stride, but we also do need to talk about the padding, okay? And what's this concept of padding? Well, the idea is that if you can zero pad your image to basically preserve the size spatially. So for example, if I have a 7x7 image here, which is in yellow, and then I zero pad it, okay, which is basically put a bunch of zeros on the outside of it. So it technically becomes 8x8. With a filter of 3x3 and a stride by 1 with a zero pad of 1, the output's actually 7x7. In other words, I will keep the exact same image size because I went ahead and zero padded. Same thing happens if I zero pad by 2 with a filter of 5x5. Okay, so again, stride of 1, zero pad of 2, output 7x7. So this particular case, it's saying I want to go ahead and have, from the convolution perspective, I actually want to keep the padding the same. So in other words, I want to keep the image size the same as the output. So the common practice you'll see is a stride of equal to 1, filter size is f by f, zero padding f minus 1 divided by 2. So that's typically what your common practice is. And so looking at those common practices, how that translates to inside your TensorFlow code, basically stride is equal to 1, so there's your 1 by 1. Your filter size of f by f, in this case 5 by 5, and your zero padding of same, which basically indicates you want the same size, which is the f minus 1 divided by 2, okay? So that's how that code that you've written in your TensorFlow code here, okay? And this is actually from a TensorFlow sample that you could get directly from the TensorFlow site. In the notebook that we provide that has all the images and all this other information, we have a direct source to the TensorFlow code as well too. So we have everything all nicely packaged up for you, okay? And so, all right, so that's that part of the code. Now let's switch a little bit because we're gonna talk about activation functions here, okay? Now, The activation functions is that once you compute the output of the neurons, the dot product between the weights, okay, remember that we also need to go ahead and determine if it passes a threshold or not, and such that the output will go ahead and actually fire to go to the next set of neurons. Okay, so let's talk about this ReLU step that you see here. And that's actually the ReLU code that you actually see inside, because we've chosen the ReLU activation function as our function for our convolution neural network. Okay, so same concept of everything you see here, but right now we're focusing specifically on that activation function part here. Okay, all right. So basically, it defines the output of the node, i.e. your artificial neuron, based on your given inputs. It maps to a resulting value between 0 and 1 or -1 to 1, depending on which activation function you're using, such as the sigmoid function. So remember, when I did the shredder example, that's what I did. I applied the sigmoid function to get the value between 0 and 1. Okay, so in this case, there's a value of 0.75. Okay, and so activation functions basically are this. It started with this concept of like a step function, right? Basically it was 0, and then once you hit at some point, it jumped up to 1, okay? That's a good starting point, and basically it's your bias or threshold activation function, right? But then you hear more about sigmoid and tanh. They introduce a nonlinearity to your activation function, which is good. But the problem is that for both of these is that as you got to the extremes, whether the value was low and the value was high, basically it would start saturating, so that became slightly problematic. And so then the concept is ReLU. ReLU is one of the more popular ones because it's simple to compute and very robust and to noisy inputs. Okay, so that's the reason why right now, as of today, you will see ReLU as one of your more popular activation functions. Now note that there are other activation functions, leaky ReLU or whatever else, that are coming into play. And actually, we did discuss a little bit this in the previous 3 sessions. So if you want to dive into more about that, please look at the other 3 sessions where we do actually discuss more about those activation functions. But right now we're going to focus on that because that's the way we wrote the code, right, in terms of the ReLU activation function. Okay, and so back to the code. There you go. Basically, TensorFlow.nn neural networks.ReLU. That's the activation function. So that first set of code that you see for your deep neural network, this H_convolution1, basically it's calling ReLU as your activation function, which calls that function called convolution TD, where you define your strides, you define your padding, you define your bias, prop them together, and then there you go. That's how you calculate for your first activation function, for your first convolution layer via the ReLU activation function. Okay. All right. So taking a little break, switching gears. Now let's talk about pooling. All right. Not the pool table pooling though. We're going to talk about pooling, which also is known as subsampling. Okay. So the concept of pooling in this case is that we're actually trying to perform a downsampling operation along the spatial dimensions W and H, resulting in a reduced volume. Okay, so in other words, what originally was an image of 28 by 28 now gets reduced to a 14 by 14 image. In other words, we're trying to get smaller and smaller and smaller. So the whole concept of our neural network is that we end up having more and more smaller 14 by 14, right, images, okay, and as we progress between the convolutions, pooling, okay. So now let's focus on the pooling itself. All right. So like we noted, pooling is equal to subsampling, which is equal to the reduction of the image size. Okay. So we have a single depth slice here. Okay, X and Y here. We have a max pool with a 2 by 2 filters and a stride by 2 for sake of argument. Because we are pooling also uses those same concepts of stride and filters. Okay. Because it does, this 4 by 4 image becomes a 2 by 2. Okay, because it's using a 2 by 2 filter and a stride by 2. Okay, so that's now a reduction by 2x because it's 4 by 4 now down to a 2 by 2. Right, this is us going and shrinking down the size of the image. Okay, All right. It's common to insert pooling layers between successive convolutional layers. The idea is to reduce size spatially, reduce the amount of parameters, and minimizes the likelihood of overfitting. You'll remember in your machine learning concepts that when you overfit, what's great about overfitting is basically for the data you have, the model you have is going to be perfect. The problem is it's not a generalized model, right? What will end up happening when you overfit is that this model will work extremely well for the data you have, but any new data that you bring in, this model actually doesn't work well for. So the goal is to build a generalized model that can do a solid job, high accuracy, low loss. So when you're doing, when you're running your model, it's able to go ahead and do a solid set of predictions on your generalized set of data. Same concept applies to our deep learning or to our TensorFlow concept here, that we want it to be able to, our model to be able to read those handwritten digits in a generalized manner as opposed to be super precise with the data that we've got, okay? And so, again, minimizes the likelihood of overfitting. Okay, perfect. All right, so that's why we're shrinking it down, right, to prevent that from happening. Now, a thing to note is that while it's common to insert pooling layers between successive convolution layers, there are different architectures that are in play. This was actually discussed in the previous part 3 session more deeply. But the concept that comes into play is that there are different types of architecture designs. And as you progress in working with CNNs or just neural networks in general, you'll end up having more and more interesting architectures that have maybe only convolutions. Because don't forget, convolutions, for example, can actually shrink the size of your image too. If you actually don't zero pad or you have a slightly larger filter, remember how I could get that 32x32 image down to 28x28 by just using convolutions of using a 5x5 filter. I can do something like that. So for example, the 2015 winner of the ResNet award, the ImageNet award using ResNet actually had, I think only something like 2 pooling layers. It actually had majority convolutional layers, and they used the convolution layers to actually shrink down the size of the image, okay? Now, that's not to say that you always want to do that. I'm just simply saying that, you know, while it's common to use pooling layers, understand that you can still technically use convolutions to go ahead and shrink down the size of your image too, okay? And that may be able to achieve the same goal that you want to hit, okay? So what are your pooling common practices here, okay? So your inputs, W1 times H1 by D1, your width times height times depth, okay? Your output is W2 times H2 times D2, where, well, there's the calculations. You know, where basically W2 is W1 minus the filter size divided by the stride plus 1, D2, the same depth, and H2 is the H1 minus the filter size divided by the stride plus 1, okay? But in a nutshell, typically your filter size is equal to 2, your stride size is equal to 2. Sometimes you can do overlap pooling where your filter size is equal to 3 and your stride size is equal to 2, but pooling with even larger receptive fields, basically a larger F or a larger S for that matter, it's too destructive. And what that means basically is that you lose too much information too quickly as you're processing that data. So that's why typically you're going to stick with this F2 equals 2 or S equals 2 when you're working with your pooling, okay? All right, so let's see. And so there's the code right there. So when you look at your code inside your pool, there's actually really 2 sections. One is this right here on the bottom here, pooling layer equals down samples by 2x, H underscore pool 1 equals max pool 2 by 2, all right? Well, the max pool 2 by 2 is basically a function that really just simply calls the TensorFlow neural network max pool, where the K size, the F, okay, is 2 by 2, and your stride is also 2 by 2, okay? So in other words, your F equals 2 and S equals 2, that's what we called out on the previous slide. That's your F equals 2 and S equals 2 right here. And again, same concept with padding. We're using the same padding size because we're actually not zero padding this. Sorry, we are zero padding this. And so that's why the padding is equal to the same. But the more important concept is the K size, kernel, stride size, and they're both 2 by 2 in this particular case, okay? All right. So let's see here. Okay, so if we were to sort of put this all together, stride, pooling, oh my, okay? Smaller strides result in larger outputs, okay? Larger strides equals smaller outputs, which, means less overlaps. The great thing of larger strides is that it's less memory is required, okay? And it minimizes overfitting, okay? So that's a good thing. The downfall of larger strides is that you may overdo it and you might lose some information. So typically what you want to do is you want to actually have multiple convolutional, then convolutional pooling, so that way you don't lose too much information too quickly, so your model actually ends up being more accurate, okay? And so like I called out, oh, actually, I forgot that I even wrote this down before, but exactly like I just called it before, potentially use larger strides in convolution layer to reduce the number of pooling layers. So you don't necessarily have to do convolution pooling, though that's our example. And like I noted, ImageNet 2015 winner, ResNet has actually only 2 pooling layers, okay? All right, so now let's go to that fully connected layer. All right, so the fully connected layer basically is when we now take the output of our pooling, convolution, all that stuff together and take all the previous layers, and what we do is basically actually do finally connect them all together, prototypical of your standard artificial neural network, okay? And so the output of something like this basically is, something like these little square dots. In this case, is to represent the value 3. Because it's like a 0 array here, but that's more or less the concept, right? Now that I take all the information from the output from everything that I've put together, all right, now go ahead and fully connect it and let me see if I can use that information to figure out what my value is, okay? So what's the fully connected? Okay, so the fully connected layer is that after we go ahead and 2 rounds of downsampling, our 28 by 28 image has shrunk down to 7 by 7 by 64 feature maps. This maps to 1,024 features. Because it maps to 1,024 features, inside the code, again, we called this out, W_FC1, that's the weight variable. It's 7 by 7 by 64. That's what we have. We have a bias variable of 1,024. 1,024 features, excuse me. Sorry. And I forgot to put a blue square here, next to the weight variable as well. But basically, the pool flat, where we're going to reshape that, what we're reshaping it to, again, it's a 7 by 7 by 64 feature map. Okay, and then our ReLU, our activation function, is actually doing a matrix multiplication of your pooled flattened array. Okay, so that's what happens, right? What we before is that we have these 7 by 7 images in essence, if you think about these, but these are of course numbers, arrays, matrices, right? And you have 64 of them, right? But now we're going to flatten them out, okay? And so that's what this matrix multiplication is all about, all right? All right, but now we wanted to talk about, oh, okay, great, I've done all this math, but how do I optimize this? Okay, and so and if you guys aren't seeing it, this is Optimizer Prime, a la Optimus Prime. Bad joke, but I figured I'd toss that in there. Okay, so when you look at this entire thing, what we've shown so far is we've taken the input, run a convolution, run a pooling. There's actually a second convolution, second pooling, but those are the exact same concepts as from the first time, so that's why I didn't repeat that. It just said we shrink it down from 28 by 28, ultimately to 7 by 7, okay? We want to run faster, so we're going to go ahead and do batch iterations of this, right? So, okay, so these batch iterations basically is this. Now, this is the code. This is the key code components that you're going to see, again, inside the code base you've got. So you've got your batch, you've got your training to run it. Inside there is your TF train ADA delta optimizer and your accuracy evaluation. So you're going, okay, great. What does this all mean? Okay. What this means is this. The batch is the iterations. We're going to go through this multiple times through each and every single batches of images to try to make our model run faster and better, okay? And so the training steps is all of this. We're going to go run all this code, okay? So all the code that you saw before in terms of the convolutions, the pooling, convolution pooling, fully connected, brought that all together, basically this is what we're doing is we're going to calculate the accuracy of it. So in essence, what we're doing is we're saying, okay, how accurate is it when we do those steps of convolution pooling, fully connected? That's what the accuracy is, okay? What we're also doing is we're also calculating the loss, all right? So the loss is basically how much are we losing in the process? So we're trying to minimize the loss and we're trying to increase the accuracy, okay? So in that concept of the loss, we're doing a softmax, okay? Softmax basically is it's the concept of us doing a softmax regression. That's when we go ahead and finally determine when we're doing comparison of the digits that we have, the output, excuse me, and we're trying to figure out is the value 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That multi-step logistic regression basically is a softmax regression, and so that's what that softmax refers to. And how we optimize it, in this case, we're using ADA delta. Now, there are other different optimizers that you can try. In fact, the original code uses Atom, okay, but I altered it to use ADA delta. Atom's actually perfectly fine as well, but if you go back to our part 2 and part 3 of our webinars, we actually dive into a little bit more on why one particular optimizer works better than the other. Now, to provide a little bit of a primer so I can sort of give that concept here, basically, in practice, the Atom in general, whether it's ADA delta or Atom, right, is currently recommended as your default algorithm, okay? And often works slightly better than RMS prop, okay? However, it is often also worth trying SGD versus Nesterov as an alternative. This is sort of the general rule of thumb to play with. But that's why when you look at the sample code in TensorFlow for this, that's why it's using Atom right away, right? Because it's saying, well, you know, in general, Atom's the default optimizer algorithm we work with. And so if you were to visualize optimization and from a concept of a lost surface contours, you'll notice the yellow and the blue, which is ADA grad and ADA delta, are able to go from the starting point and get to the end point, the global minima of your lost surface contour, the fastest. The black one is next, and that's RMS prop, which is exactly what Andrei Karpathy, this is the previous slide, was referring to. Saying that, you'll notice that actually the purple one, Naj, Nesterov actually does a pretty good job. It does go out of course first. It goes completely the wrong way, but it quickly, speedily gets back to it and catches up, and actually in some cases might even beat ADA delta, even though it went to the wrong contour first before it went to finally find the global minimum. Okay, so this is this is the key problem with momentum-based methods, the SGD momentum Nesterov, that they often overshoot, go to the wrong place before they go there. But it's still a good alternative, and that's why the quick call out here. Okay, and so another way of looking at it is optimization on a saddle point. You'll notice again in yellow, which is ADA delta, it just shot down the fastest. Okay, boom, right away. You notice the black and purple, that's black is RMS prop, that is actually extremely fast, and the dark purple, which is referring to ADA grad, blue, it goes ahead and shoots down extremely fast as well, and it finds its path, while SGD, actually stochastic gradient descent, actually gets stuck at the top for a while before it actually is able to finally come down, okay? So these are just visualizations of different optimizations, but the concept in the end is that there are different optimization techniques that will come into play that allow you to go ahead and improve the performance and optimize the performance of those batch iterations of you going ahead and doing those steps of, you know, convolution pool, fully connected, okay? And so now let's go fully into just demo now, back to the code itself, all right? And so for the remaining 3 to 5 minutes here, you can look at the code here. And I've already run this code, but you'll notice basically, like I said, the graph is right here, okay? So you can see what the structure of our convolutional neural network here looks like, okay? The functions that we talked about, the conv2D, the max pooling, all that is right here. And it, again, is this code that we actually grabbed as I scroll upwards directly from TensorFlow. I took the 1.12 version of it because that's when I wrote it at the time. Okay, so but this is a key call out. We happen to be running this on Databricks Runtime 5.1 for our machine learning. The reason why is because this actually pre-installs TensorFlow for you, so it's already pre-optimized. So if you happen to be running Databricks, that's awesome. Go ahead and run Databricks Runtime for ML, and then all the machine learning libraries, whether it's TensorFlow, PyTorch, whatever else, they're all a scikit-learn, they're already pre-installed for you, okay? If you don't have that, by the way, it's actually pretty easy. You just attach a library to the cluster. The instructions are included in the notebook, and using PyPy, and specifically you would add TensorFlow, okay? So saying that, also, again, all the inside this notebook, not only do we have the code, but we also explain, so that image that you saw inside the notebook, inside the presentation, that's included here. So to explain, you know, what the training sample data looks like, what the test sample data looks like. The code that you have here, the model is right here. Okay, so again, the description and all that stuff's right here. When you the code that we went through line by line, basically that convolutional layer, that pooling layer, fully connected layer, all of it's all here. Okay, so hopefully by combining for yourself, by combining the notebook that you have here and the slides, you'll be able to sort of go back and forth and look at the code and follow the code via the slides, so that we can see how this operates and how this runs, and how changing these things ultimately impact the accuracy and loss of your neural network, of your CNN. Okay. And so again, we have your training the model. Note the fact that basically by default, it comes with the in the original code base, it was with the Atom optimizer. I'm using 88 delta, the optimizer, but I put both values inside there so you can actually make use of it. Okay. And also the other little key thing that I added here was also that you could specifically run using GPUs by basically this call out. So with TFS device, specifically call out that now I'm using the GPU as opposed to the CPU to do my training ones here. Okay, so I already ran this, so that way you don't have to wait for the 2.87 minutes to go ahead and take a look at it. But when I've executed this entire thing, basically you'll see each step, and this is each step as it's going through the batches of images, these images of handwritten digits, it's determining the accuracy. Now step 0, of course, it's 0.02, but it already jumps up to 0.92, and then it just back and forth. And as it goes through each and every single step, it'll go ahead and see if it can, how much higher that accuracy is going to be. So it sticks 1, 0.98, yada, yada, yada. But then when we test the accuracy of it, basically, this is us going and running this little bit of code. Basically, we figure out that it actually has a 0.992 set of accuracy, which is not bad, okay? So using the code that we just described that runs a convolutional neural network, what ultimately we have actually is a pretty cool way, or pretty efficient way, for us to use a CNN to accurately, pretty accurately go ahead and build a model that can predict the handwritten digits and what number that ultimately turns out to look like. Okay, and so this is a simplistic example, obviously, but hopefully by showing it this way, you can able to use that example and play around yourself, so you can change the strides, the padding, and things of that nature to work with the code. Okay. All right. So let's go ahead and stop the screen share and go back to the slides here. All right. I do want to thank that there are many other people that have been extremely helpful. For starters, of course, Data Science Central. They're a great organization and extremely helpful, and we love working with them. There's some great references that I wanted to call out. They're all here in the slides, so just as we noted, you're more than welcome to, if you don't, to ping us, and we'll give you the slides and have access to them, because these slides, we want to share them so you can make use of them, okay? And all the references that we have, we've highly attributed, obviously, the slides themselves, but the direct references, just in case, are right here, okay? Other more great references of whether it's the convolutional neural networks class by Andre Kaparthi, or specifically the white paper on ADA delta, and also things like the backpropagation with TensorFlow, and so forth and so forth. So these are great references for you to work with. Another great reference is this one, which is the CovNet.js MNIST demo. So this is just a great way to visualize everything you said, we just talked about today, for you to take a look at that and run accordingly. And finally, I did want to go ahead and, in addition to Data Science Central, thank Tom McDrabus, Brooke Winnig, Timothy Hunter, and Cyril Simon for their great help. They've been crucial to ensuring that we can always produce some great content in coordination with Data Science Central. And with that, Bill, I will return it to you.
Well, Denny, hey, thank you for that great presentation. And we'll get started with today's Q&A. And I want to thank the audience for their participation. We had a lot of questions that have come in. And we'll do our best to get through all of them in the time remaining. So during this Q&A session, I'll leave up this screen contact with contact information for Denny if you'd like to get a hold of him following today's webinar. And so let's get started. Denny, let me start by asking, you offered to make the deck and the notebook available. Should folks ping you at this email address shown on this screen?
Absolutely. They can ping me directly on this email, and or I believe we'll be reaching out to folks who have attended session and provide actually the links to it directly to the slides and the notebook as well.
Oh, terrific. Okay, good. All right. So, real questions. Starting with the more general ones. Audience is asking, okay, what's the basic? Why are we using CNNs instead of regular neural networks on images?
Oh, no problem. And we discussed this a little bit, but let me make sure that I've clarified it just in case I did not discuss it properly in the beginning. And by the way, we did discuss this more in depth in the second webinar of our DSC Deep Learning Fundamental Series, the training neural networks. But the concept is that convolutional neural networks, or CNNs, are similar to regular artificial networks, except, and here's where the exception is, they make explicit assumptions that that the inputs are images. Because of that, the issue is that it's not fully connected. Okay, when you're dealing with artificial neural networks in general, it's typically a fully connected layer. Every single hidden layer is talking to every single other hidden layer node. It's talking to every single input layer node. In the case of a CNN, because it won't scale well when you're talking about that many different pixels, that many for your image, we don't actually try to look at, we don't make it fully connected, at least not in the beginning. We actually go ahead and only look at a smaller portion of, this is why we talked about convolutions and kernels and filter size, to basically shrink it down. So we only look at a local, we sort of call it local connectivity, but the idea is a local portion of that image, and do our convolution against that. And then as our layers are convolution and pooling, the pooling shrinks down the image, as our layers of convolution pooling, will over time shrink down that image. So that way, at that point, we can switch from your, in this example, some by some image of 64 feature maps into 1024 feature maps, and then that can become a one-time fully connected layer to basically run our softmax regression to say, okay, is the number we're seeing a 0, or is the number we're seeing a 9, or whatever else? Okay, so ultimately that's the concept, that CNNs make explicit assumptions that the input we're dealing with are images. Hopefully that answers the question, Bill.
Yeah, absolutely, Denny. That was perfectly clear. Thank you for that explanation. So you started it off by using TensorFlow, and you explained that TensorFlow was enormously popular. Is there some particular reason why Keras or PyTorch would not be as good to use for CNNs?
Oh, that's a great question. And so in the case of Keras and PyTorch, in fact, no. You're more than welcome to use Keras and PyTorch. In fact, the first 3 sessions of our Data Science Central Deep Learning Fundamental Series, we were actually using Keras as our primary example. Keras actually is a little bit easier to work with because it's a higher abstraction layer. So it actually simplifies simplifies it versus using TensorFlow. And so you can use Keras, for example, with the TensorFlow backend. You're still using TensorFlow, but you're using Keras instead of TensorFlow to make your life easier. Keras also has things like, as an example, you know how in the TensorFlow code, I explicitly called out I wanted to use a GPU. Well, in the case of Keras, if a GPU is already there, it'll automatically use it by definition. And so there are things like that that are involved, that are included in Keras that are awesome and makes your life a lot easier. And so by all means, if you're starting off or just would like a simpler abstraction layer and you don't want to get into the nuts and bolts of it, by all means, Keras makes a ton of sense. TensorFlow don't get me wrong, I'm not trying to knock TensorFlow. TensorFlow is great. That's why we have this session today. TensorFlow is more if you want to really start altering the nuts and bolts at a much deeper level. And that's why this particular session was the way it was, where we're starting to get into what does that code mean. And while we did not discuss PyTorch, no, PyTorch is a great framework to work with. While we don't have in this deep learning fundamental series, we did not talk that much about PyTorch. There are numerous PyTorch examples that we have in which we're doing running neural networks. And for that matter, you're more than welcome to email me. My email's right there, and I can send you some of the examples that we do right away. PyTorch is a great framework, and in fact, those three, Keras, TensorFlow, and PyTorch, are pretty much my number 1, 2, and 3 right there. So great question. I don't think it's wrong to use any or either, and often I will see it'll be common to just use one versus the other just because you felt that way, or the code sample had to be more easily available.
Hey, Denny, thank you for that comparison. Now, here's a question that, way back when I started with CNNs, got me the first time I looked at it too. And way back at the beginning of your example, you showed the MNIST handwritten characters, and they were in grayscale. But you talked about RGB values. Would you explain about depth and why we talk about RGB even if it's grayscale?
Oh, no problem at all. So when we say RGB, yes, we're talking about red, green, blue. Now, in this particular case, you're right. The MNIST actually is a grayscale image. So we're actually, in this case, not talking about red, green, blue. So I probably implied something I wasn't meaning to imply. It's just more like in general, if you've got an image, and an example of a 3-layer depth is basically to talk about red, green, and blue. That was the concept. But you're absolutely right. In the case of this MNIST example that we're dealing with grayscale, but the depths of your image doesn't necessarily have to be color channels. It can be other channels that are coming into play. And just because they're gray doesn't mean there aren't other components coming into play that aren't necessarily your prototypical red, green, blue as well. And so the call out is that typically it's more like when you're saying your image, you have a width, you have a height, or length and width, right, for your image, and you have a depth. And the depth is basically the filter or feature maps that you're working with. And so in this case, basically, you're right. While it's not the 3 color channels we're talking about, it is other channels that are coming into play to basically to provide some form of depth against our MNIST example. Hopefully that clarifies that explanation.
Oh, yeah, Denny, I think we've got time for one more quick one. And I thought this was particularly interesting. And that is, are filters ever defined as anything other than square? For example, could they be 7 by 5 or 3 by 5?
Oh, that's a great question. And it is plausible to do it, but not usually in the form of convolution networks. I've seen non-square filters happen for other neural networks, and even then, it's typically very hard to do it. So, but especially within the concept of convolutional neural networks right now, traditionally we are working with square size filters just because it allows us to be able to, from a mathematical calculation perspective, it's easier for us to apply the convolution, it's easier for us to apply the stride, it's easier for us to apply the padding and things of that nature. It doesn't preclude us with the ability to not do it, but that is without a doubt the most common approach that we typically work with.
Well, hey, Denny, thank you. Those were some great answers to some very good questions. And for those of you that asked questions today that weren't answered, we'll be sending all the unanswered questions to Denny and the Databricks team so they can follow up with you after today's webinar. Now, I have just a couple of quick announcements. If you'd please mark your calendars for January 31st, and that's our next DSC webinar, which is Optimize the Data Supply Chain. Now, remember also that today's taping will be available for on-demand viewing. You can find that later today on the home page of Data Science Central in the Webinar tab located at the top of the page. And by the way, all our past webinars are also available on demand at datasciencecentral.com. And if you haven't had the chance to look at them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Well, this brings today's webinar to a close, and I'd like to thank our audience for their attendance and thoughtful questions. A special thanks again to Databricks for their sponsorship, and particularly our speaker today, Denny Lee, for his insight into today's topic. This is Bill Vorhies. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on January 31st. Have a great day.